This video is going to talk about Newton's laws of motion, and we begin in the beginning with the first law of motion, which you were introduced to in the last video. We define inertia as a resistance to change in motion, which leads to the previously made statement that an object in motion tends to remain in motion, an object at rest tends to remain at rest, and there is a requirement for there to be an outside force to cause a change in that motion, or rest states. So Newton's first law, briefly restated from the other video, is that Newton's first law, an object in motion will remain in motion, an object at rest will remain at rest until acted upon by an outside force. There are other ways that this law is occasionally formulated, and it is also referred to as the law of inertia. And we'll talk about some of those other formulations in the future. A model of change that is very useful talks about the ratio of the action, the thing that is causing the change, to the resistance to that change. So the amount of change can be increased by having a larger action, or it can be decreased by having a smaller action. Similarly, the amount of change can be decreased by having a larger resistance, or increased by having a smaller resistance. And the ratio of those two things, the ratio of action to resistance, tells you how large the change is going to be. The action, which is a somewhat old-fashioned word in a physics context, but is still used, is the cause of the change. In our case, we're going to apply our change model to the concept of acceleration. Acceleration is a change in motion. That change can be a change in speed, or it can be a change in direction. The acceleration is proportional to the force that caused it, and inversely proportional to the resistance to that change, the inertia. So the first law describes inertia as a resistance to change in motion. The second law describes the change in motion as the ratio of the applied net force, the total force acting on the object, to the inertia of the object. And as I alluded to earlier, inertia has a one-to-one correspondence to the concept of mass. The amount of material is directly causative of the resistance to change in motion, and therefore force to mass ratio is equivalent to the change in motion, which is what we will be referring to as the acceleration of the object. Newton's third law deals with the nature of the forces. And in this case, every action produces an equal and opposite reaction. And the reason for that is forces are always the result of the interaction of two objects, and you can have multiple interactions with the same object, so you can have forces provided by more than two objects. But there's an inherent symmetry in nature. When you have an object exerting a force on another object, there is always a symmetrical reaction force as a result of that first action. And if you think about this at a sort of molecular level, at an actual true microscopic level, the individual electron clouds around the molecules of the interacting objects have no way of knowing whether they're on the pusher or the pushee, so there needs to be a symmetry in those interactions. And that leads us to Newton's third law. For every action, there's an equal and opposite reaction. We characterize a number of different kinds of forces that we're going to look at in physics: gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. In the first semester, we're really dealing with the first two, although we generally don't look at the details of the electromagnetic interaction until the second semester. We instead look at the macroscopic interaction. But we know in modern times that if you have a spring, that spring is made out of a collection of atoms that are all interacting with each other, and we see that as a single large object, but in reality it is a multitude of extremely small objects interacting with each other electromagnetically. Chemistry takes place at the electromagnetic level. The weak nuclear force governs certain kinds of radioactive products, and we'll look at that a little bit towards the end of the second semester, but it doesn't make very much of an appearance in the first semester. The strong nuclear force is responsible for holding nuclei together and overcoming the strong proton-proton repulsion. What we think of as nuclear energy is a result mostly of the strong force. There's also some still very poorly understood force, which is generally referred to as the dark energy. Now, the gravitational force between two objects is a very common thing in our lives, so we have nicknamed it weight. Weight is a force exerted by gravity, and we tend to think of this in terms of the Earth pulling on you. But there is, of course, a symmetrical pull of you pulling on the Earth. The manifestation of gravity that we see is gravitational acceleration. We fall. And symmetrically, the Earth falls. But if you think of Newton's second law, the difference becomes quite clear. The Earth's inertia is enormous, on the order of 10 to the 23rd, 10 to the 24th times as large as your inertia. So when you fall 1 meter, the Earth falls 10 to the negative 24 meters. Significantly smaller than the diameter of a proton. So we don't measure the falling of the Earth, although it does fall symmetrically to your fall. The acceleration for all bodies relative to the Earth turns out to be the same because the inertial mass, which resists changes to motion, is equivalent to gravitational mass, which increases with mass in the same way. So if you are twice as heavy, you have twice the force acting on you, but at the same time, you have twice the resistance to the change in motion. So in the context of things falling near the surface of the Earth, we have the gravitational acceleration being equivalent for all bodies. Written out formulaically with Newton's second law, that means our gravitational acceleration, which we pretty much universally abbreviate lowercase g, is the ratio of weight to mass. And this highlights the importance of distinguishing between weight and mass. So, to cap off, we have Newton's 3 laws of motion, and we have looked at one application of that law of motion, which is the gravitational acceleration produced by the Earth or some other large object exerting a force on some mass. Next, we will look at some applications of forces and force vectors.